Hi everyone. In this video we are going to cover the first part of section 14.4 titled the normal distribution. And these bullets tell us what we're going to do throughout all of section 14.4, but in the first of three videos, the first of three videos, we're just going to deal with something called the empirical rule and describing the basic properties of the normal distribution, and then also interpreting things in terms of area and percentages a little bit. And first, of course, what is the normal distribution, right? A distribution is just, what a data set looks like as a histogram or as a tally table. A distribution is just a collection of data, all right? But the normal distribution, it describes many real-life data sets. That's why we kind of use the word normal. Real-life data sets tend to look normal. A histogram, the histogram shown gives an idea of the shape of the normal distribution. So you have your highest frequencies in the middle of the distribution, and then you kind of trail off in a somewhat symmetric manner as you go out from the center. So if we look at the distribution of, say, heights of males in their 20s, most males in their 20s, the highest frequency in the middle will be what most males are, and then some males are taller, and way fewer, are way taller than the mean, right? There are very few 6'8", 20-year-old males out there. Similarly, there are very few 4'7" males out there that are in their 20s, okay? We have the highest frequencies in the middle for men, and then trailing off in symmetric ways on either side for many real-life data sets. And then we're going to use, we used X bar and S for mean and standard deviation. When we're talking about populations, we tend to use the mean is this Greek letter mu. I think I mentioned that in an earlier video. And the standard deviation is sigma. All right. And so for the normal distribution, the mean, the median, and the mode all happen to be packed right close next to each other in the center because of the symmetricness of the distribution. All of those measures of center are actually in the center. And so if we remove the boxy histogram from the picture and just have the curve that is the normal distribution, right? If you have enough data points, then your histogram starts to take on this shape, right? Your histogram will never actually look like a smooth curve, but it kind of follows that path, okay? These points here are referred to as inflection points. If you ever take calculus, you'll learn about inflection points. We don't need to be super concerned with that word, but the mean in the middle, and as you add and subtract the standard deviation, the distribution tends to follow this pattern. And it's in the homework problems, and it's sometimes referred to as the 68, 95, 99.7 rule, or it's also known as the empirical rule. The empirical rule. Like that. There we go. All right. And what it says is that if I have a data set with some mean and some standard deviation, then if I add and subtract that standard deviation from the mean, then 68% of the data falls within that interval, right? So if we knew the mean and standard deviation of 20-year-old males, 68% of them are shorter than this height and taller than that height. They fall within that interval. Similarly, 95%, if I add and subtract the standard deviation twice, 95% of 20 to 30-year-old males, or whatever I said at first, males in their 20s fall within two standard deviations of the mean. So if you had a group of 100 males in their 20s, right, 95% of them would be between those two heights, whatever they happen to be. And then the last one, 99.7. So virtually all of the data will fall within 3 standard deviations of the mean. Okay, and we'll draw this distribution with a real example in just a minute. But that's those percentages. They can then be broken up. And so like because it's symmetric, here we go. I have 34%, that's half of 68, and 34% on either side of the mean, right? And if you do a little subtraction and a little division, right, you'll find that 13.5% is in that interval, and 13.5% is in that interval. So if you add the 13.5, 34, 34, and 13.5, you get 95%. Then if you take the 99.7 minus the 95 and divide by 2, in that little interval, not much data there, but it's 2.35% of the data is in that interval. Similarly over here, 2.35% of the data is there. And then the last, if you subtract 0.3, or if you subtract 99.7 from 100, you get 0.3. And then cutting that in half, we get 0.15% is beyond 3 standard deviations above, and 0.15% is beyond 3 standard deviations below. So very few individuals in my data set will fall outside of 3 standard deviations. 0.1% is 1 out of 1,000, right? That's not that many. And so here we have our properties of the normal distribution. It's bell-shaped. Some refer to it as a bell curve. It is symmetric. Okay, so that means it's the same on both sides with respect to the mean. So the half the data is above the mean, half the data is below the mean. Then the mean, median, and mode of the distribution are the same, or if it's a real data set, they're like super close together. The total area under the curve is 1, which allows us to apply these 3 different percentages to the distribution. Because we say that the area is 1, then we can break it up into the 68, 95, and 99.7% rule, the empirical rule. All right, now let's look at an example and see how we make this distribution. So in this example, we have a distribution of scores of 1,000 students. So we have 1,000 individuals. They take a standardized intelligence test. So we want to see who's the smartest, or just how smart they are. If the distribution's mean is 450, standard deviation is 25. How many scores do we expect to fall between 425 and 475? How many do we expect to fall above 500? Really, the purpose of this example is to say, how do we make this distribution? How do we set it up? And then how do we use it to answer questions about the data, about the individuals? All right, so let me move this up a little bit here. So what I'm going to do first is draw my bell curve, and I'm going to make a horizontal line like that. And then I'm going to go up and back down like that. And it's not perfect. I shouldn't have crossed my horizontal line here, but hopefully you get the idea. Sometimes I only do erase it and draw it again. This one turned out okay. All right, and what we do is I'm going to draw a dotted line for the center of my distribution and label that with the mean, which is 450. So 450 is the mean because they tell me that in the problem. I'm going to put my little mu there. All right, and then as I go out, I'm going to draw dotted lines because it helps me to keep track of things. I'm going to go 1 dotted line, 2 dotted lines, and then 3 dotted lines like that. And if I were more of an artist, it would look the same on both sides. They wouldn't have the scribble on the right-hand side, but I mean, hopefully we get the idea. All right, so to create the other labels on this distribution, I'm going to add and subtract the standard deviation, which is 25. So 450 plus 25 is 475. That's mu plus sigma. Add it again, I get 500. That's mu plus 2 standard deviations. Add it one more time, and I get 525. That's mu plus 3 sigma. I'm going to do the same thing on the other side of the mean. Subtract 425. Subtract again, 400. That's mu minus 2 sigma. Subtract one more time, and we get 375 mu minus 3 sigma. All right, so that's how we create the distribution. All right, now we apply the empirical rule, the 68, and I'm going to write it down again, actually. We're going to apply the 68, 95, 99.7 rule, or the empirical rule. The question says, how many scores do we expect to fall between 425 and 475? How many scores? All right, so where's 425? It's right there. So this line here, and 475 is right there, that line like that. How much of the data falls there? Well, that's 1 standard deviation below, 1 standard deviation above. So we know for part A, let me move it over a little bit like that. For part A, we have 68% fall within 1 standard deviation. I'm going to abbreviate standard deviation there, 1 standard deviation. So how many is that? Not what percent, how many is that? What is 68% of, 1,000 students? 1,000 students. To answer that question, I'm going to take decimal point 68, so convert my percent to a decimal, times 1,000 of, that means to multiply in math. 0.68 times 1,000 is 680 students. Okay, so if the mean is 450, standard deviation is 25, we expect 680 of the students to have scored between 425 and 475. All right, part B, what about those, oops, that's supposed to be a B. We'll make it a B like that. What about those really exceptional students? How many scores do we expect to fall above 500? 500 is right there. So I want to know let me change colors actually. We'll go green. I want to know how many scores fall above 500. Now there's a couple of ways to get this percentage. We could write down the percents that were in here and here from the previous slide. We could use some subtraction, right? There's a lot of different ways to approach this. I am going to go ahead and write down the 0.15% that I had on the previous slide and 2.35%, okay? And we'll add those up. 2.35 plus 1.15 is 2.5% fall, 2.5% score above 500. Above 500. So what does that mean? How many students is that are those really exceptional students that took this test? 2.5% of 1,000. Oops, that's 10,000. So let me just scribble out one of the zeros. There we go. 2.5% of 1,000, 0.025 times 1,000 is equal to 25 students. So 25 of the students that took the test out of the whole 1,000 that took it score above 500 and had that top score, you know. That's how you use it. Oh, actually, before I finish this here, you could have also, let's say I didn't remember what those were, okay? Maybe I knew that, excuse me, that this is 34 and this is 34%, right, as I had on the last slide. And maybe you also remember that this is 13.5%. 13.5%, right? I could take 100 minus 50 to get rid of that half of the distribution, because I know I'm only looking over here, and then take the remaining 50% minus the 34 minus the 13.5, and just in case you can't figure out what those two different percentages should be, there's a couple of different ways to figure it out. All right. That is actually the end of the video. This is the end of part 1 of 14.4. So there will be 2 more shorter videos to go through the rest of the section. But give this homework a try and let me know if you run into any problems. Thank you very much for listening. Have a wonderful day.